Hi, welcome back. Long time no see. Today we are going to be discussing the first type of important sum in number theory, and that is just Gauss sums. But before jumping into this lecture, you have to recall everything what you know about characters. You can watch just the previous lecture and refresh everything you learned. Throughout this lecture, I'm gonna denote this number e raised to the power of 2 pi I over p by this letter zeta, which is a standard notion in complex analysis. And furthermore, I'm gonna need this result, which is written right over here, which I'm not gonna prove today. So if you take zeta raised to the power of at and you sum over all t from 0 to p minus 1, then this sum is going to be equal to 0, providing the fact that this a is not congruent to 0 modulo p. In other words, p does not divide a. Otherwise, if p does divide a, then this sum will be just equal to this number p. So now it's time to define so-called Gauss sum. But before, we have to take any character he from this group, and also we will take an arbitrary element a from this field fp again. Then we just take this character at each point t running over all elements from this field and multiply this by this aforementioned zeta raised to the power of at. And this sum will be just denoted by this g with this little a, and here we just specify a character, and this is known as a Gauss sum. By the way, you can rewrite this sum in a more convenient way. You can just write this as t goes from 0 to p minus 1, as we did right over here. But, for the sake of a fashion, I'm just using this notion fp every single time, so why can't I use this notion again right over here? So you see that this definition is, well, kind of inconvenient for us, because this sum depends not only on which character you specify, but also it depends on this letter a with this element from this field. And if you watch carefully what this sum represents, well, this is also a headache for us. You just have to compute every single character at each point and then just somehow add every single element with this zeta raised to the power of a times t, which is, for me, ridiculously difficult. However, there is one result which simplifies our computation a lot. There it is. So, in fact, you can evaluate this Gauss sum in the following way. You just want to evaluate just Gauss sum with this little 1 here. So instead of a, you just plug 1 right over here. And then you just multiply this sum by this character at point a inverse. Well, this sum will be a little bit simpler to compute. However, this formula is applicable only for the case when this character is non-trivial, and furthermore, this a is not 0. So this formula is convenient just because we restrict our attention to Gauss sum at point 1. So we just remove one dependency, and we have the only dependency right over here. Now what about the rest of the cases? So if we still assume that this character he is non-trivial, however this time a is 0, then this Gauss sum will be just equal to 0. Or you can do vice versa. If your character is trivial but you still have a non-zero element a, then you will still get 0 in this Gauss sum. There's only one case left when a character is trivial and a is 0 simultaneously. For this case, we get the fact that this Gauss sum is just going to be equal to this prime number p. So we automatically computed the Gauss sum for the rest of the 3 cases right over here. Let's try to prove every single case. So each case will be labeled by those Roman numbers 1, 2, and 3 respectively. So here we just want to prove this equation, providing the fact that our character is non-trivial and this a is non-zero as well. However, in fact, we can actually show, instead of this, we can actually prove that if we take this Gauss sum and multiply by he at point a, then we must get the fact that this is just a Gauss sum at point 1 with this character he. So I just wrote the same equation but for this case I just multiplied both sides by he at point A, and this will be vanished as just 1. I hope you understand what I just said. So let's start rewriting this left hand side. So if we take he at point A and this Gauss sum, we just substitute this Gauss sum with the following expression, and then I just put this he at point A inside of the sum, leading to this expression. We just sum over all elements from Fp, but this time he at point A times t, because of the fact that he is a multiplicative stuff. And then I just take this zeta and raise it to the power of at. And now you notice that this expression at repeats every single time, so why don't we use a substitution? So let me just denote this a times t by letter s, and since t runs over all elements inside of this Fp, and luckily a is not 0, then it means that this s will also run over all elements in this field, but maybe in a different order. So thus we still sum over all elements in Fp, and this time he is computed at point s and zeta is raised to the power of s, and I deliberately wrote here this number 1 times right over here just because to make a juxtaposition. So if you just take this expression and put right over here, you will notice that this object is nothing but a Gauss sum, but instead of a we just write 1, and then we take this character he. So that's what we needed to show for the first case. Here's the case number 2 we have to check. So this Gauss sum is equal to 0, providing those two conditions. And now we should investigate each of them separately. So let's suppose that a is 0 and the character is non-trivial. Then in this case we compute Gauss sum with a equals 0. So this is just he at point t times zeta raised to the power of 0 times t, which is just 1. So I can get rid of this thing. And notice that we sum over all possible elements from this field, and we just compute character at each point right over here. And by previous lecture, by a previous result, you have to know that this sum is just nothing but 0. And now we do vice versa. Suppose that this character is trivial, but a is non-zero. In this case, we again write this Gauss sum in the following way. So we compute this trivial character at each point times zeta raised to the power of at. But this trivial character at each point is just 1, so I can get rid of this. And now I'm only left with this zeta raised to the power of at. And since a is not 0, so p does not divide a, we just have to recall the first result right over here, and you will see that this sum is actually 0 just for another reason. In one of those cases, our Gauss sum will be equal to 0. Finally, the third case, when we have the fact that this character is trivial and the number a is 0 at the same time. Let's try to write this Gauss sum, and you will see that this is just trivial character at point t, so this is just 1 times zeta raised to the power of 0t, which is again 1. So we just sum all ones, and we have exactly p ones, because we have p elements right over here, so this sum is just p. That's what we needed to show. This is our QED. From now, I'm gonna denote this Gauss sum at point 1 just by g with this character he. So I just remove this number 1 over here just for the sake of maybe simplicity again. There is one interesting estimation we're gonna apply for the next time, just in order to find the total amount of solutions in some equations. And that is, if you take this Gauss sum, where here we assume this is number 1, but we just do not write this anymore, and take any character he, non-trivial one, this thing with the absolute value is going to be equal to square root of p. Make sure you understand that this Gauss sum is just a complex number, so we just take the absolute value of a complex number. The secret of this result is the fact that we have to consider this sum where we take Gauss sum at this character and then we do the same Gauss sum, but we take its conjugate since this is a complex number. And we just make this sum running over all elements in this field. And we're gonna compute the sum with two different ways so that we reach this equation. The first approach here is when we apply this result what we've proved. So we're gonna substitute this Gauss sum at point A with this character as the character with A inverse times this Gauss sum with this character here. But we don't really need to write this one anymore by this remark. But this equation holds for the case when A is not 0. The character is already non-trivial, so everything is fine. Now, if A is 0 right over here, then we have the fact that this G0 with this character here times G0 with the same character conjugate, we know that this is going to be 0 because at least one argument is 0, this one, and the character is non-trivial. By preceding result, this is just 0. Whereas if A is not 0, then we can apply this formula right now. So when A is not 0, we just substitute each Gauss sum with the formula mentioned a few seconds ago, and then we have the following expression. Now you have this complex number, you just separate this conjugation, you conjugate first of all this one, and then this object. And now just recall the property that if you take a conjugate of this character, this is the same as he at point A inverse. So in our case, if I take A inverse here and conjugate, then I get A inverse inverse, which is precisely just A. So this is just he at point A, and we multiply this by he at point A inverse, which is just he at point 1, and this is precisely 1. So we are only left with these two Gauss sums. But you multiply Gauss sum and its conjugate, so you get that this is just the absolute value of this complex number squared. So this is the first way how we computed this sum. And the first way corresponds to the left-hand side of the equation. Well, almost, because we have this second power, but anyways. And now, if this one term is equal to this absolute value of Gauss sum squared, then if we go back to this sum, so I just Ctrl-C and Ctrl-V this one, then you will notice that, well, the first term is 0, and the rest p minus 1 terms are going to be just this absolute value. So totally we have that this sum is equal to p minus 1 times this absolute value squared of this complex number. Now the second way how we compute this sum, we just directly insert our definition of Gauss sum. So instead of GA at point here, we just put here a sum how we defined above. So here I just plugged the definition of Gauss sum. So instead of this, I just put this sum, and instead of this, I put the same sum. But I want to differentiate those elements because there are two independent sums that I compute. And now let's take a look at this sum. You just take sum and the whole thing is conjugate. If you take two complex numbers and you conjugate them, then it's pretty clear that you can just sum those numbers and take conjugate separately. Nothing will be changed. So this sum can be written as you take conjugate for each term. So you plug this conjugate here. Not for the whole sum, but for this term. And this, since we multiply both complex numbers, we can just again separate this conjugation like this. So you conjugate he at point t, and you conjugate this complex number zeta raised to the power of at. But recalling what this zeta means and how we conjugate this number, this will be just nothing but zeta raised to the power of negative at. Now I would like to multiply this thing with this one, and this just corresponds to the following expression. You just take a double sum, run with this s over all elements in this fp, you take the same with t, and then you just take this term and multiply by this term. So you get he at point s times he at point t conjugate times zeta raised to the power of as and zeta raised to the power of negative at. So this can be written as zeta raised to the power of as minus at as 1 power. And now no one forbids me to change these three sums in the following way. So I just write this in the following way. So I first sum by this element s, then I sum by this element t, and then I sum by this element a. And I just insert here the same terms. Now, since this expression does not depend on this a, so I can just factor out of this third sum in the following way. So I just put this sum here and then plug this expression right over here, leading to this sum, which looks kind of similar to this sum what we mentioned from the beginning. Now, throughout this discussion, I'm gonna ignore the case when s is either 0 or t is 0. The reason is because if s is 0, you get he at point 0, and you get that the whole thing is just 0. Likewise with t equals 0. Now, since we sum with this element a over all elements, then this sum will be dependent only on this bracket s minus t. And if s minus t is not congruent to 0 modulo p, then this sum will be just 0. Or if it does congruent to 0 modulo p, then this sum is just p, as we mentioned at the beginning. But this expression s minus t is between negative p minus 1 over 2 and p minus 1 over 2. So in order to make this element congruent to 0 modulo p, then there is only one case when s is equal to t. So when s equals t, then this sum is just p. For the rest of the cases, this sum will be just 0. Now the main question is, how many times does this case appear in this sum? Ignoring the case when s0 or t0, then we have that st might be 1 simultaneously, might be 2 simultaneously, and so on and so forth up to p minus 1. So we have p minus 1 total possibilities when s is equal to t. So we get p minus 1 copies of this p. And for the rest cases, this is going to be just 0. So this total sum is just p minus 1 copies of this number p and nothing else. So it means that this sum is just going to be equal to p minus 1 multiplied by p. So if you apply the first approach, you get that this sum is equal to p minus 1 times this absolute value squared. And if you take the second approach, you will get that this is just p minus 1 times p. So totally you have this equation, and you can reduce both sides by p minus 1, leading to this expression that this number squared is just p. So this absolute value must be equal to square root of p. And this is our QED right over here. Now I should maybe mention one more thing. So we have proven this equation, but turns out this can be rewritten in another way. So first of all, I'm gonna square both sides of this equation like this, and then just try to recall that every single complex number with its absolute value and squared can be represented as this complex number z times its conjugate. So I'm gonna rewrite this as this Gauss sum times the same Gauss sum, but this time is conjugate, and this is still is equal to p. Now I really would like to consider this Gauss sum conjugate and see in detail what this is equal to. So taking this Gauss sum conjugate, you will see that this is just again sum running over all elements from this field. You take conjugate here at point t times this zeta raised to the power of negative t. And now I want to make this equal to he at point negative t instead of t. So I can just rewrite this he at point t by the multiplicativity as he at point negative 1 times he at point negative t. Now let's just conjugate both sides of this equation and concentrate on this. So you know that if you take character at each point conjugate, then this is the same as taking character at this point inverse. But you know that negative 1 inverse is the same negative 1. because -1 times -1 is just 1 in our field FP. So you can just write this as he at point -1. And now you can rewrite the sum as follows. So you take this sum running over all elements in this field, then you take he at point -1, he at point -t conjugate, multiplying by zeta raised to the power of -t, and finally, since this object does not depend on t, you can just factor it out. Well, I ran out of space, never mind. Now if you watch carefully, so I factored out this he at point -1, and the rest thing, if you consider another character, he bar, which is by definition a character at point t conjugate, then you will just notice that this sum is just the same as the Gauss sum, where we sent a character he conjugate, which is defined in the following way. So going back to this equation, plugging this thing, we will see that this Gauss sum times the same Gauss sum, but we put a character conjugate, times this character at point -1 is just p. But you can multiply both sides by this character at point -1, so if you multiply here, you get just character at point 1, which is precisely 1, and on the right hand side you will get this character at point -1, and thus you found another equation, which is also an important one, and we're gonna apply this later. Here's the final example, and this is a special case of Gauss sum, which has another name, which is called Quadratic Gauss sum. This time, instead of picking any arbitrary character, we're gonna take a specific character, which is known as Legendre symbol. You already know about this, and you just sum over all elements of this FP, and you take this Legendre symbol t modulo p and multiply this by zeta raised to the power of at. And for this Gauss sum, you have still the same results as we had above, but in the next lecture we're going to be talking about this quadratic Gauss sum in detail, since there are more informations hidden. So stay tuned. He at point -1 conjugate is the same as he at point -1, and you take inverse of this element. But you probably know that -1 inverse is just 1. So this is just he at point 1, which is precisely... Wait, what? So each case will be labeled by those Roman letters. Wait, what? If it does divide, then this sum will be just equal to this number p. Recall this result, which is important for us. Да блин!